Hey everyone, I'm out by this beautiful lake right near my house because today's topic is rods. And that obviously must mean fishing rods. Now to me, one of my favorite things about fishing rods and why I'm so excited for this topic
Hey
today.
Mike,
Yeah, what's up?
I was just looking over the course syllabus here, and I don't think this lecture is supposed to be about fishing rods.
Then what's it supposed to be about?
Well, I was just doing some research, and I found this topic area called stepped rods, and that seems to include things like stress, strain, and internal forces and material properties.
Oh, that does sound way more applicable to the class than fishing rods.
Yeah, that's kind of what I was thinking.
Does that mean I bought all this fishing gear and everything for nothing?
Yeah, probably.
Damn! Pack it up. Hey everyone, back in my room after being out at the lake, and I have to apologize for that little snafu earlier and that little bit of confusion. Today's lecture is not on fishing rods, but is actually on rods of different materials with different steps in them that we'll be analyzing using all the concepts from stress, internal forces, and material properties. So to go over kind of the lecture today, it's going to be a pretty short one. We're going to talk about stepped rods, which isn't really any new technical material. It's just a lot of the application of the older material we've done in the previous lectures to a new type of statics problem. So we'll be dealing with stepped rods, which tend to look something like this in the example below. You can have both 2D and kind of three-dimensional stepped rods, but we'll be looking at the second kind in 2D. And really, what a stepped rod problem is it's going to combine everything you've learned in internal forces, stress and strain, as well as material properties. So we'll be looking at these rods that have different forces applied on them, and different parts of the rod may be stretching or compressing, and you'll be kind of bringing all of that together to understand the system as a whole. If you're wondering how are you going to apply this stepped rods material to the real world, well, consider the example below. Imagine you find yourself one day in an intergalactic trash compactor, and you've got to try and jam something in between the two walls that are slowly closing in, trying to crush you. That's kind of what we'd be dealing with here, because you can actually see in this example the rod that Luke and Leia and that other guy, whatever his name is, are trying to put in between these two walls of the trash compactor has different cross sections. So in a way that's similar. I know it's a bit of a stretch, but that's something at least that I've recognized in the real world that is like a stepped rods problem. So pretty much what I want to do in this lecture is just jump straight into some handwritten solutions and show you how you apply all the concepts you've learned so far to these types of problems. The first problem we'll look at is the one that's shown below. Pretty much what you've got is two rods here, rod ABC, which is made out of aluminum, and rod CD, which is made out of steel. Pretty much you're told all these different material properties like Young's modulus, Poisson's ratio about these materials, and you're asked to determine a variety of different things, which is the normal stresses on the rods, the total change in length of the whole system, and to calculate change in diameter. So again, nothing is new here per se, but really what we're doing is applying all the concepts to a new format of problem. And before we get started with this, let me show you really quickly what steps you're going to want to take in a stepped rod problem. In a stepped rods problem, you're going to want to follow a certain set of steps, because not only does that make sense with the name of the topic, but it's also because most stepped rod problems follow a very similar solution path, pretty much. So what I've done for you to help make your life a little bit easier is put together this step-by-step guide below that will help you follow these steps to solve the stepped rod problem. Sorry for all those steps. But pretty much the first thing you want to do in a stepped rod problem is make a cut through all of the points that either A, fall between two different letters, or B, fall between two different forces. In this particular case, the points that meet that condition, where we want to make our cuts, are going to be between points A and B, between B and C, and between C and D. Now, people always just think, oh, it's always just between letters. But consider this for a second. If we got rid of point B and just made the rod A, C, D, I think a lot of times students or people might think, I only have to make one cut through A and C and one cut through C and D. But a good and silly way to visualize where you need to make cuts is not just the letters, but imagine putting yourself in the problem. And you in the problem are either being squished, so you have to push out to fight being squished, or you're being stretched, so you have to pull back in to fight being overly stretched. So a good way to think about this is kind of put yourself in different parts of the stepped rod and think about what you might be experiencing there. So for example, if we look at section CD, we can see that the only thing that rod CD is experiencing is a 10 kip pulling out. So what that probably means is that that rod is going to be stretched. Because that rod is stretched, that person is probably pulling in to fight that. But if we look at the section BC, which maybe the letter B wasn't there, if we looked in between those forces there, we would see that the 15 are going in and the 20 is going in as well. So we might guess that if we were there, we might be feeling squished. And then between A and B, we're also on the other side of forces, so we might feel a different balance of things. The 20 wouldn't be going in towards us, it would actually be going away from us. So that's a really good strategy to figure out where you might need to cut in a stepped rod problem. The second step you'd want to do would be to choose which way to look. And almost always, you're going to want to follow the same conventions that you used in internal forces, and you'll want to look away from the wall. Because remember, at the wall, you're going to have 3 unknown reaction forces, AX, AY, and a moment of A. So in this particular case, you're going to want to look to the right in all of these cases, because you'll avoid looking at the supports, which you don't know that are at the wall. After you do that, just like in internal forces, you'll draw the free body diagram of each of your cuts, but we do have one difference. You do not care about the shear force or the moment, the bending moment inside. The only internal force we're going to be drawing and worrying about in stepped rods is the normal force. So keep that in mind, and when we go through the example, you'll see how that works out. After that, you'll solve for the internal normal forces that you've got. So we'll have a PAB, a PBC, and a PCD as well. You'll use your sum of the forces equations, and you'll solve for those things. And the last and final step you'll take in a stepped rod problem is to check the given conditions. Usually in a stepped rod problem, you'll get conditions to the effect of, what's the total elongation of the rod ABCD? Or, is the diameter of section BC increasing or decreasing? So take the summation of all the different internal normal forces and things that you've learned, along with the material properties conditions, and kind of figure out whether or not your system meets the conditions that are outlined at the beginning of the problem. Now that you've got this step-by-step solution guide, what we'll do is we'll go through a handwritten solution, and you'll be able to see how this applies to that problem, and hopefully that will help give you an idea of how you'll approach this and future stepped rod problems. So in this particular case, we're told we have 2 cylindrical rods, ABC and rod CD, and they're both joined at C and are subjected to the axial loads. We're given Young's modulus and Poisson's ratio for both of our rods, and we're told the initial diameters for both of our rods as well. The 3 questions that this problem poses are A, to determine the normal stresses in each section of the rod, B, find the total change in length of the whole rod system and to determine whether the whole length increases or decreases, and part C, to calculate the change in diameter for part CD only. And we're asked whether or not the diameter for this increases or decreases. So a qualitative question. So the first step in every stepped rods problem, as I've explained, is you want to make a cut through every single section of the rod. Now you always want to make a cut through sections with letters. So we're going to make a cut at AB. We're going to make a cut in between B and C. And even if this letter B hadn't been here, we would still make this cut here because we can tell that section AB and BC, although it's the same rod, is going to experience different forces because there's this internal force going right there. So we draw one through BC. We kind of look from C to D. There's no internal forces here, but we do have 2 letters, and there's different end conditions. So we'll draw one more dotted red line to indicate a cut at that section right there. Now, almost always, you'll want to take your cut and look away from the wall. And the reason is because the wall is a fixed support. It has 3 unknowns there. So we want to try and avoid that at all costs. So we want to cut and look to the right for each one of these sections here. Once we've made the cut lines, what we now do is we draw a free body diagram for all three of those particular spaces. Now I've drawn the free body diagram for section CD, section cut BC, and section cut AB. Here, here, and here. Now we'll go through and we'll do some of the forces to figure out what is the forces experienced, the normal force, inside of each one of these sections of rod. So if we look at section CD, we can do a sum of the forces in the x direction, set that equal to 0, and what we'll see is that we have 10 kips to the right minus PCD. What this tells us, pretty simply, is that PCD is equal to 10 kip. We'll repeat that process for section BC. So doing a sum of the forces in the x down here, we set this equal to 0. This will be negative PBC minus 15 kip plus 10 kip. And what we can see is that PBC is going to come out to be 15 minus 15, negative 30, plus 10 is negative 20. Brought to the other side, we'd get negative PB equals 20. So we get that PBC here equals 20 kips. And we can say that this is negative because this beam is going to be in compression. Now going back up above, we see that PCD is in tension. It's being pulled apart. So we'll just add a little T circle here to indicate tension. And I'll even write that here as a little note as well for the notes later. Now we can go to this free body diagram of AB. We'll repeat the same exact process. We'll do some of the forces in the x direction. We'll set that equal to 0. That'll tell us negative PAB plus 20 to the right minus 15 plus 10. We'll solve this equation for PAB. What we see is we get 20 plus 10 is 30, minus 30 equals 0. So we actually luck out a bit and find out that PAB has 0 force inside of it. So it's neither in tension or compression. It just turns out that all the forces to the right balance out. Now that we know the internal normal force of all of our sections, CD, BC, and AB, we can now answer these three questions. So to answer question A, we're told to calculate the normal stress in each section of the rod. So the normal stress in section AB is going to be equal to PAB over the area of AB, which we know is going to be equal to 0. So sigma AB is just 0. That's easy. Then we can solve for the sigma of section BC. Sigma BC is going to be PBC over the area of BC, which is going to tell us that we've got PBC, which is negative 20. So we put negative 20 on top because it's in compression. That's negative 20 kips, by the way. Divided by the area of BC, we can see that the diameter up in this section of the rod is 2.25 inches squared. So we'll say that this is pi over 4 times the diameter, 2.25 squared. What comes out of this equation here is that sigma BC is going to be negative 5.03 KSI, or kilopounds per square inch. And that's our answer for sigma BC. Now we'll look at sigma CD, which again is just PCD over the area of CD. PCD, we said, was 10 kips and it's in tension, so we plug in a positive 10 kips on top. The area over here, we're going to use the diameter of 1.75. So we have pi over 4 times 1.75 squared. And we find that sigma CD is going to be 4.158 KSI. And that's a positive value because that piece of the rod is being stretched. So we've now solved all of part A, and we can move on to the other parts of this problem. Part B asks us to find the total change in length of ABCD, and it asks us whether the length of everything increases or decreases. So what we're going to do is we're going to say that the change in length of ABCD is going to be equal to the change in length of section AB plus the change in length of section BC plus the change in length of section CD. Now, what we can do is realize that the change in length of AB is going to be 0 because it has no stress inside there, so it's not in tension or compression. So the change in length of our whole bar is going to be the change in length of BC plus the change in length of section CD up here. So now we can solve for each of those change in lengths. So the change in length of section BC is going to be equal to Fl, which is P of BC times the initial length of section BC divided by the Young's modulus of the material of BC times the area of BC. So we know that PBC is negative 20, so we'll plug that in there, negative 20 kips, times the initial length of BC is 8 inches, so we plug in a value of 8 right here. We'll divide that by Young's modulus, which we're told is 30 times 10 to the 6th psi. We're going to plug in rod ABC, which is 10 times 10 to the 6th psi. But we want to convert this to KSI, since we're using all of our units are kips. So if we have 1,000,000 psi, that means we have 10,000 KSI. We can say the same is true for this down here. 30 times 10 to the 6th becomes 30,000 KSI. So Young's modulus here is going to be 10,000 KSI times the area of BC, which is pi over 4 times 2.25 squared. This tells us that the change in length of section BC is going to be negative 0.00402 inches because it's in compression. We can now repeat this process for section CD right here. So we say that the change in length of CD is going to be equal to 10 kip times the initial length, which is 15 inches, divided by 30,000 KSI times the area, which is going to be pi over 4 times 1.75 squared. And ultimately what this tells us is for that the total length of change CD, we get that it increases its length by positive 0.00208 inches. Therefore, to answer question B, the total change in length of ABCD is equal to these two numbers added together, which is negative 0.00402 inches plus 0.00208 inches. And this gets us a value that the total rod decreases in length by a value of 0.00193 inches. And this is equal to the change in length of ABCD. Now I've run out of room on this piece of paper, so I'm going to move to another sheet and we'll answer question C. Now what we'll do is we'll calculate the total change in diameter for section CD, which is this piece right here. I've written down the main things that we knew from last time. I realize not all of this is important, but I did it anyway. And we're asked to determine whether the diameter increases or decreases. Well, what we know from before is that PCD is in tension. So if our rod is in tension, that means the rod is being stretched. When the rod stretches, the cross-sectional area will slowly decrease until that material snaps and pulls apart. Because our change in length of CD is also positive, that's another way that's indicating that the rod is being stretched. So we know that regardless, that the diameter is going to decrease in size as the rod stretches. Now, we're asked to calculate that change in diameter. So the way that we do this is we use Poisson's ratio. And we know that Poisson's ratio is equal to the strain in the transverse direction over the strain in the axial direction. This essentially can be rewritten as the transverse strain is the change in diameter over the initial diameter, all divided by the change in length total of that section divided by the L initial. So we know all of these things here. We were told the Poisson's ratio for section CD is 0.3. So we have 0.30 is equal to the change in diameter, which is what we're looking for. So we have change in D divided by the initial diameter, which is 1.75 inches. Divide that by the change in length of section CD, which we found to be 0.00208 inches. And divide that by the initial length, which was 15 inches. And what we can see is that the only thing we don't know in this whole question right here is this value of change in D. So solving for the change in diameter of CD, we find that this is a value of 7.28 times 10 to the negative fifth inches. So that's a very small change in diameter. That's our final answer. And what we get is that because this rod is in tension, this will be a decrease in diameter. So there you go. That's how we did this stepped rod problem. Just to review, I'll bring in the other sheet of paper. The solution methodology that we follow is make a cut in each section of the rod. Here we had to make 3 cuts in between each of the letters, or in between every time that there's a change in forces being experienced. So we drew free body diagrams for section AB, BC, and CD. We did sums of the forces to put the internal normal force of each section in context of the other applied forces. So we found that for everything. Then we solved for the normal stress in each section of the rod, which is what we were asked for in part A. We then did a change of length of everything using the rearranged formula of Young's modulus for change in length. We then added those values together and found the change in length of the total rod. And last but not least, we used the change in lengths from the previous section and our knowledge of Poisson's ratio to find the change in length of one of the sections, which was length CD. We found the change in diameter there, and because again this is a rod that is in tension, this piece right there, which we know from part A and B, the diameter will decrease. And that is how you do an internal loads problem.
Let's take a look at this problem, which is just another stepped rod problem. And here we've got rod ABC. We're told it's 2 rods, one of steel and one of aluminum, and we're given some conditions at the bottom related to total elongation and normal stresses. And the interesting wrinkle in this problem is that the bar is not horizontal, but it's now vertical, and that we're not actually given all the applied loads. So in this particular question, we're actually asked to solve for the maximum applied force that can be given to this system with satisfying all the conditions that are laid out. So what we'll do is we'll jump to the handwritten solution, and I'll show you how we approach this problem right here.
In this problem here, we have a stepped rod problem, which really is a problem that combines internal forces, stresses, material properties, and a little bit of statics as well. In this particular question, we have 2 rods, AB and BC. We're told that rod AB is made of steel. We're given its value of Young's modulus, its initial length, and its initial diameter. We're told the same things for rod BC, which is right here, and we're told that that's made out of aluminum. We're told that the rod is loaded with 2 sets of forces, the 30 kip forces here on this plate B, and this force P here that's pulling down. Now we're assuming that everything is kind of attached together. We're ignoring this thin junction plate at point B, and again, we're making sure that we assume that all of the materials remain in a linear elastic region, which is the point before the material would reach sigma yield and actually deform permanently. The 2 constraints that we have is that the total elongation of this whole system is limited to 0.05 inches, and that the normal stresses in rods AB and BC should not exceed 35 and 15 ksi respectively. We're told also to assume a safety factor of 2. So the question we're asked here is, find the largest load P that can be given to satisfy these conditions down below here. Now the first thing you always want to do in a stepped rod problem is draw a free body diagram of your 2 stepped rods.
And the way that we do that is we'll be using very much similar concepts to what we did in internal forces, which is we're going to want to make a cut through this rod and through this rod at the top. What we do is we'll draw our red dotted lines to cut through both of these rods, both AB and BC, and we'll decide whether we should look up or whether we should look down. Now, you can see that the cut we make through rod AB, we're going to want to look down because, again, we want to be as lazy as possible and choose the side with the least unknowns. That would be looking down because the only thing we would see would be P. If we looked up, we would have seen this 30 kips, and 3 reaction forces up here, which would have been CY, CX, and a moment. So we don't want to look that way, and that's going to also hold true for rod BC. We're going to want to cut through the rod and look down, so that way all we see is these 30 kip forces here and this P. So now that we've made both of these cuts, I'm going to draw the free body diagrams of both of those systems, and then we'll get started with the rest. Now that I've got the free body diagram of AB and BC, we can look a little bit closer and see what we would do next. So if we look at rod AB, we look down, we see the cut P, and then we see PAB, the normal force, going out. Now the way that rod problems are different than internal forces problems is that we're only going to be looking at the normal forces inside the rods. We're going to disregard the shear and disregard the internal bending moment. We're mostly focusing our efforts on determining whether the rod is stretching, compressing, or things like that. So as a result, we look only at the normal force, and given our XY axes as shown here, it's pretty clear to see that when we do a sum of the forces in the Y, we're going to find out that if this piece is at rest, then we're going to have PAB up minus P. Well, this tells us that the applied load P that we're looking to solve for is going to be equal to the force that's felt inside of rod AB. So this is going to be important later on. When we look over here and we do a sum of the force in the Y on rod BC, our free body diagram shows us that we have PBC going out of the rod, which we always assume this. We're drawing it in a positive tension. We see we've got 30 kips going this way, and we've got a P going down. So if we sum the forces in the Y on this particular free body diagram, what we'll see is PBC plus 30 minus P. So we don't know whether PBC is actually going up or if it's going to point down, because it's possible that if this P got really large, the PBC would be up, but if this P was 0, for example, PBC would be 60 pointing down. So in this case, we just kind of want to solve for PBC, and we say that PBC is going to be equal to P minus 60. Now that we've got both of our internal loads, PBC and PAB, in terms of the applied force P that we want to figure out, what we'll do is now check these conditions. So condition number 1 is that the total elongation of the rod is limited to 0.05 inches. So I'm going to check this condition, which is the total deformation condition. So to check this condition, what we use is the rearrangement of Young's modulus formula, which tells us that the change in length of rod ABC is going to be equal to the change in length of section AB plus the change in length of section BC. We can rearrange this equation right here using the Young's modulus, which will tell us that the P of AB times the length of AB initial divided by the Young's modulus of the material of AB times the area of AB plus the same for BC. PBC times LBC divided by EBC times ABC. ABC, woo, easy as 1, 2, 3. All right, so now that we've got all of this, we can see down here that we've got PAB in terms of P, we've got PBC in terms of P. We know the initial length of both rods here, so we know this term. We know the Young's modulus for both rods, here and here. And we know the diameter of both of the rods, so we also know the cross-sectional area. This is the one thing that we don't yet know, which is the change in length of BC. But what we do, because our limit is 0.05 inches, we say that this is 0.05. So then the one thing that we don't end up knowing yet, really, is this P over here. And by taking these two values right there, plugging them into their respective equations, we'll be able to manipulate this equation up top to keep everything in terms of one unknown, which will be the applied force P right here. So let's plug in everything that we know and see what we get. So what we can see now is we've got 0.05 is going to be equal to PL over EA for both of our materials. And we've taken these two values over here and we've plugged them in respectively for PAB and PBC. What you can see is that our one unknown is P. So what we're going to be able to do is actually solve this equation right here for P. The one tricky thing that kind of comes out of this is that over here we've got P minus 60. This means that you're going to have to distribute P across all of these different terms and 60 across all of those terms. But what I would do first is take 30, divide it by Young's modulus and the area, and then take that one value and distribute it times P and times 60. And ultimately what you'll get after doing all of the math for this is that P max, to ensure that we don't exceed 0.05 inches of elongation or stretch, is going to be 88,900 pounds, which is 88.9 kip or kilopounds, 1,000 pounds. And this is condition number 1. So that's how we do the first part of this question, but now we need to understand whether or not the condition 2 is met by this force or something greater or smaller. So now we have to check condition 2, which asks us to check the normal stress in AB and BC should not exceed 35 and 15 KSI respectively. So assuming a safety factor of 2, we'll set up this condition down here and solve. So by looking here, we're going to check that we don't exceed the normal stress limits. And we have to use a factor of safety of 2. So remember that safety factor is equal to the max of the material over the design, which in this particular case, we know that the safety factor is going to be 2, which equals the maximum, which is 35 KSI, or 35,000 PSI for rod AB, over what we're designing for. So what this tells us is that the design we should use to calculate the P is going to be equal to 17,500 PSI. And this is the design sigma, or sigma design of AB. So if that's the case, we know that sigma AB is equal to PAB over the area of AB. The limit that we're setting is that this is 17,500 will equal PAB, which we say is equal to P, so we plug in P, divided by the area of AB, which is pi over 4 times 2 squared, or diameter squared. And what this tells us is that P max for this particular question is 55 kip. So this is P max number 2, condition AB, that we've just found, is 55 kip. Following the exact same protocol here, what you can see is that if our sigma max for BC is 15 KSI, with a safety factor of 2, we'll follow the same exact procedure, and you'll find that sigma BC design, our limit, is equal to 7.5 KSI, or 7,500 PSI. And we'll set that equal to PBC over area of BC. Now we know that 7,500 will equal this now instead of PBC. So we say P minus 60, and this is 60 kips, right? So what we'll say is P minus 60,000, because this is PSI, divided by the area of BC, which is pi over 4 times 3 squared. This tells us here that P max for condition number 2, rod BC, is going to be equal to 113 kip. Now our last and final question that we have to answer for this whole problem is, which of these 3 forces is the maximum P that we can provide? Well, if we apply more than 88.9 kips, then our rod would deform more than 0.05 inches. If we applied 55 kips or more, then we would exceed the limit in this particular case, which is we would exceed the normal stress that's allowed in AB. So right now, 55 is less than 88.9. So if we applied 70 kips, sure, we would have satisfied this condition, but we would have failed under this condition right here. So right now, 55 is our limiting factor. If we look, PBC has a maximum value of 113 kips, was allowable before we get 15 KSI in that rod right there. So as a result, what this means is that 55 kips is the lowest possible force of the whole thing that satisfies all conditions. So this is our true final answer right there. And what you can see in this type of problem is for a rod, just to reiterate, the steps you take are make a cut through each section of rod, or sometimes there'll be forces inside here. Like for example, there could be a force right there. You would want to take a cut through here and here if the force was inside of AB. But you'll take cuts through at least every lettered section. You'll draw free body diagrams of those sections, do sums of the forces. Then you'll use material properties conditions or stress conditions, which you see here, everything we learned in Unit 7 and 8, to solve for the normal forces or applied forces in our system. And that is the general format and flow of a rod problem.
That's all I've got on today's lecture for stepped rods. Hopefully it was short and sweet and to the point, and you've gotten to see how we apply concepts from earlier in the class to this unit to solving stepped rod problems. See y'all next time.
Next lecture's supposed to be about rods. What could that mean? Maybe it's curtain rods.
In today's lecture, we're going to talk about one of the most important and most commonly overlooked design elements in your home. The curtain rod.
No, that can't be it. If it's not curtain rods, what else could it be? Oh! Wait a minute. Fishing rods. That's definitely what it is. Let me see if I can buy some fishing gear. Got some good ideas for a video. Nice. Crushing it, Mike. Students are going to love this.